All right, let's look at a couple of definitions here. All right, so first one is set of all linear combinations. All right, let's say you have a subset D of a vector space, and when you say FD, F being the field that we are using, all right, then FD is the set of all possible finite linear combinations. That means that of course all the coefficient AI's are from the field F, and the vector VI's are from the set D, and then you take a linear combination. But we only take a finitely many linear combinations, and you take all possible linear combinations and throw all of them into a set. That is what the FD is. Right? So FD is the set of all linear combinations of vectors in D. Right? So that's the first definition. And the second definition is a little bit strange, but we're talking about the sum of subspaces. Right? So let's say you have collection of subspaces of V. Right? So W1 Wi's. Right? Then the sum of all those Wi's, so sum of those subspaces, all right, is the set with the sum of all the elements. So you take one element from, actually first, you take finitely many of Wi's. So capital lambda is just a finite non-empty subset of the index set omega, right? So you take a finitely many Wi's and you pick an element from each one element from each one. Then we add them all up, right? So you collect all those possible, the sum of those elements here, and throw it in one set, right? But remember that if you do that, you end up taking all the possible linear combinations of elements in Wi's. So this sum of subspaces end up being exactly the same set as F times, F is the field, the union of all those subspaces, right? So the sum is really the same thing as linear combination, the set of linear combinations of the union of the subspaces. So you can take any vector from Wi's and make a linear combinations, right? And that linear combination is going to be always included in this set, right? So that's the definition of sum of the subspaces of a vector space V, right? That's it. I hope that this was clear.